Mm. Hi Santosh, is it possible to switch off this ringing sound when somebody joins in? Okay, thanks. Yeah, no, that is fine. Now it's fine. Okay, so maybe we can start then. Um, so, welcome everyone. Good morning. Today is the third and final lecture of the series on large-scale structure formation. And today, what I wanted to do is to talk a bit about how we observationally probe the large scale structure. So if you think about it, what we have done is we have already worked out some of the details on how you model or work out the theory of large scale structure, what equations you write, how do you solve them. So today we will see how to connect them to observations basically. So let's see. Now the first thing we need to understand, I mean, observationally you will observe. I mean, with your telescopes you will observe this large-scale structure. But till now, if you think about it, we have studied mostly the temporal growth of density perturbation using linear, quasi-linear, nonlinear theory, and so on. But what is still left is a discussion on the spatial distribution of the perturbations, particularly at different scales. Now, suppose you concentrate on a particular redshift or epoch. If you want to characterize the spatial distribution, you need to tell someone the value of, let us say, the density field at all spatial locations. You may also have to tell the values of the velocity field, but that only makes things very complicated. And this, of course, is kind of impossible. You will have to find out the density at every place in the universe. I mean, you are basically dealing with a large number of field values. Now, what helps us is that although we observe structures in the large scale distribution of galaxies, which I have discussed in the previous two lectures, but there is no obvious pattern in the density field. I mean, we see filaments, voids, and so on, but there is a kind of randomness in the whole thing. So, given this, we believe that the cosmic density fields, I mean, they are basically a random field generated by some stochastic process. And hence, there is no point in studying the density field location by location. I mean, if somebody gives you a specific, I mean, the density field at all locations on the sky, that itself doesn't contain, I mean, that itself is not very interesting because it is basically a realization of an underlying stochastic field. So what is useful is to study only the statistical properties of the cosmic density field rather than the density field at all points. For example, this situation arises in many other branches of physics, in particular statistical mechanics or thermodynamics, where if you think about a box containing a large number of particles, we are really not interested in the positions and the momenta of individual particles at each time, although they are moving and giving rise to whatever properties we are interested in. Rather, we study the statistical properties of the system. We may be interested in the distribution function, how are the energies distributed. We may be interested in average quantities like the temperature and pressure and so on. So, but nobody will actually go and try to calculate the positions and momenta of individual particles because that itself doesn't give us anything interesting. So similarly, in cosmology also, we are not going to go and really work out the density field in each location and try to make sense out of it. We will talk only about statistics of the density field. And if you think about it, that is what we have been doing since the first lecture. We have been talking about things like power spectrum and so on. Now, what kind of statistics are you interested in? How do we calculate the statistics? So just like in statistical mechanics, it is convenient to define the statistical properties in terms of ensemble averages. So basically, you have to mentally think of ensemble of a universe, basically. So we have our universe, which is a random realization of an underlying stochastic process, and as if there are many other universes. Those universes are not real. Okay, so you are just making copies of this universe in your mind, and each of them will have some density field which are not identical, and I've tried to show you the density field of various realizations here, some along one direction. Now what you can do is, if suppose somebody asks what is the average density at a given point, so what you need to do is you go to that point and calculate the density for all the ensembles and then average. Okay, so that we will call the ensemble average of the density field at that given point. Now, if the universe is statistically homogeneous, this ensemble average should be independent of the position. So now you see we are actually defining the homogeneity of the universe in a slightly rigorous way by bringing in this concept of ensembles. In practice, however, as I said, these ensembles are not there. I mean, even if they are there, they are not accessible to us. What we can do, so we cannot calculate this average quantities so easily. I mean, there's no way of calculating them. However, what we can do is we can calculate volume averages. So you can take a large volume and, for example, calculate the average density field there. Now, what you can show, I mean, this you can actually show mathematically, that for large enough volumes, the volume average is equal to the ensemble average. This is similar to the concept of ergodicity in statistical mechanics. So this is how we go ahead and try to characterize the cosmological density field. So I have given you the example of the average density field, but now you can go and calculate, I mean, more complicated averages. For example, you can multiply the density field in two locations and calculate their average and so on. Now, we still haven't understood what is, I mean, this is, for example, in the last slide, what we were talking about were the averages. But suppose I ask, what is the density distribution at a given point? Because at the point x1, the densities are different for different ensembles. So I can basically plot a probability distribution, and same as point 2 and point 3 and so on. But what you will realize is that if the universe has to be statistically homogeneous, these density distributions have to be consistent with each other. Now, how do we characterize this density distribution? It is very difficult to specify a general random field because it involves determination of an infinite number of quantities. Now, one good thing about our universe is that if we go and look at, for example, the CMB sky, that you can think of the initial density perturbation field, and that too when the amplitudes were small. That means the linear theory holds. The initial linear density field is very well approximated by a Gaussian random field. In the sense, the probability distribution is Gaussian. The advantage of using, I mean, if something is Gaussian, the advantage is you can basically characterize everything by its second order moments, either the power spectrum or the 2-point correlation function. For example, if you have a set of linear density contrast delta xi, which I denote as delta I, then the joint probability distribution will be given this form, basically. Okay, so this is the probability distribution of point 1 having a value delta 1, point 2 having a value delta 2, and so on, and point n having a value delta n. The probability distribution is this, which is essentially a Gaussian, but this is a very, it's a Gaussian which has a kind of n cross n terms here. Basically, it is defined in terms of this n cross n matrix, which is the average value of delta at point I and delta at point J. So that is the basic idea. Of course, the deltas at 2 points are correlated because this matrix is not necessarily diagonal. The Fourier modes, you can do the same, play the same game in the Fourier modes. And what happens is the Fourier modes too are sum of Gaussian random variables and thus form a Gaussian random field. However, they are uncorrelated. Their matrix is diagonal and hence only the diagonal term survives, and the diagonal term you will realize is like delta I, that is like delta square in the K space, and that is the power spectrum. Okay? So that is why using power spectrum has its own advantages. Now, when we go and observe, you will observe, for example, some tracer of the large scale structure. So let us say galaxies. I mean, can be anything you choose, but it has to be some tracer. So think of galaxies as the tracers. Now, the probability of finding a mass point in a randomly chosen volume, delta V, centered around some point x is nothing but rho times delta V by m. Okay, because that probability will be number density times the volume of that small cell. So that is easy to understand. But what is the joint probability of finding a galaxy at a volume delta V1 near centered around point x1 and another galaxy in a volume delta V2 centered around a point x2? What is the joint probability of that? Now the joint probability will clearly be multiplication of rho at x1 and rho at x2, its ensemble average, and then you have to multiply by the appropriate volume elements. That will be given by n square, basically the average density, and then the volume elements, of course. So at this level, it is very similar to the probability of finding one galaxy. So n square delta V1 delta V2. If that was there, that would have been easier. But there is a 1 plus psi x1 x2 term. Why does this arise? The psi x1 x2 actually measures the excess probability over random of finding two galaxies in the volume elements delta V1 and delta V2. If the galaxy distribution were completely random, then this psi would be 0. Then the probability of finding a galaxy at point 1 and probability of finding a galaxy at point 2 will be just the multiplication of the individual probabilities. And that will be psi equal to 0. So you will get n square times delta V1 delta V2. Okay. But anything over random, any excess probability over random is measured by this quantity psi. And that is called the 2-point correlation function. Operationally, suppose you had ensembles, you would have measured it using a relation which looks like this. Basically, you would have gone and measured rho at x1 and rho at x2, the density at x1 and density at x2, multiplied them. You do it for the first realization, then do it for the second realization and third realization up to n realization, and then you take an average. Okay, so that will be the ensemble average. And that will give you the 2-point correlation function. Of course, in reality, we won't be able to do the ensemble average, so we will do the same thing using volume averages. Now, this in general is a function of x1 and x2, but since our universe is statistically homogeneous, and not only that, it is statistically isotropic, what happens is xi x1 x2 first becomes xi as a function of only x1 minus x2. It's only the difference between the 2 points which matters, that is homogeneity. And isotropy will imply that even not the difference, it's only the magnitude of the separation which matters. Okay, so psi actually becomes a function of modulus of x1 minus x2. That is the 2-point correlation function. Now, you can define the power spectrum as the Fourier transform of the 2-point correlation function. And it will turn out that the power spectrum is nothing but multiplication of the Fourier modes of the density field. So delta k times delta star at k prime. But if k is not equal to k prime, this ensemble average will turn out to be 0 because of the delta function on the right hand side. So if you look at this formula, you will understand. So this formula will be non-trivial only when k is equal to k prime, and that will essentially tell you that delta mod delta k square is essentially pk, and that is what we have been using since the first lecture, but now I have defined in a more rigorous way. For statistical isotropy, what will happen is the power spectrum won't depend on the vector k, but only on the magnitude of k. So that is how it works. And you will realize that both these quantities can be measured observationally. Suppose somebody gives you a distribution of galaxies. You can either measure the 2-point correlation function using, you have to take like a pair of galaxies separated by some distance, and you have to do a volume average. Or you can do the power spectrum. Then you have to somehow take the Fourier transform of the density field and do the power spectrum, or you measure the correlation function and take its power spectrum. Okay? And you can do it for any kind of cosmological traces. Now, cosmology is very well done. The large scale structure is very well studied by the galaxy surveys. So what you do is you go using your telescopes, you measure the location, you measure the redshift or the distance, and you can then also, depending on how sensitive or powerful or what kind of properties your telescope has, you can measure things like luminosity, you can measure color, you can even take spectra if the telescope allows so. So that basically turns out to be one of the very, very, very important tasks in cosmology. And these are done using galaxy redshift surveys. And once you have these things, the large scale distribution of the galaxies will allow you to measure the power spectrum. Okay? So, for example, you can measure the slope of the power spectrum. You can measure the turnover, where it is turning over, the BAO features, and then using those, you can get the cosmological parameters. So if you look at this plot, which we discussed in the first lecture, this is the power spectrum, and these are data points. So as I said, the large scales are usually measured using CMB observations, and this intermediate to somewhat small scales are measured using galaxy surveys. Okay, so that is how things are done. Yeah. So next would be there are galaxy surveys can be used for various other things as well, because, for example, there is a set of galaxy surveys which rely on the gravitational lensing of light, the fact that the photons will get bent when they pass near to a very massive object. These studies are very useful to study the distribution of dark matter between the lensed galaxies and us. So we won't go into all the details of these surveys, but what I'm trying to say is you can do a lot of cosmology and large scale structure using galaxy surveys. So since I've started talking about galaxies, it probably makes sense to understand how galaxies form, because till now we have talked about halos, all these halos forming, dark matter coming together and then forming halos. We have discussed them using spherical collapse. We have also discussed them using, what happens in simulations, full n-body simulation. Now, as we said, these halos are there, and the gas will essentially be attracted by the gravitational force potential of these halos, and will go and settle there. Okay. So somebody is asking for calculating the volume average, which is the density distribution we assume. We don't have to assume any density distribution. You just go and calculate the densities on every point and do a volume average. So now, the gas, when it gets attracted to the dark matter potential well, what will happen is the dark matter halo has a potential. Think of that as a sphere, just for simplicity. The sphere will have some potential energy, right? So if the gas is essentially getting attracted by that huge sphere, that huge halo, it will acquire kinetic energy. Acquiring kinetic energy means the gas essentially gets heated up. And the typical temperature of this gas will be given by what we call the virion temperature. It will be essentially related to the potential of that big halo, of that big object. And for typical dark matter halos, it will turn out to be somewhere around 10 to the 4 Kelvin. Okay. Now, if the gas just goes and settles down there, what will happen is gas will also reach some kind of an equilibrium, and it will just remain there, and nothing will happen, because the density is not sufficient to trigger nuclear reactions. And if you cannot trigger nuclear reactions, there will be no stars. So what you need to do is the gas is there in the dark matter halo, but it needs to condense further. If it needs to condense further, what you need to do is you have to cool the gas. Why is it not able to condense? Because gravity would like the gas to condense, right? But it is not getting condensed because of the pressure it has, and the pressure is provided by the temperature, by the kinetic energy. So you have to find a way to cool the gas. You have to take the kinetic energy away from the gas so that it cools. If it cools, gravity will take over and it will collapse. If it collapses, it will go to higher densities, and maybe if it goes to high enough densities, some nuclear reactions will start. So that is the point. You need to cool the gas. Now, the most efficient way to dissipate energy is via atomic transition. Basically, what you can do is, if the gas particles collide with each other, one of the atoms can go to a higher excited state. Let us say if it is a hydrogen atom, maybe the electron goes from the ground state to the excited state. But it will soon come down to the ground state, and when it comes down to the ground state, it will emit a photon, and that photon will escape the system, the halo. So if it escapes, that is essentially the photon is taking some kinetic energy out of the system, and if it keeps on happening, the system will cool and hence condense. So this is how you condense. It's via atomic transition. It's called atomic cooling. There are other ways also, but this turns out to be the most efficient one. The process and this cooling will be determined by the Jeans criterion. Jeans criterion says that the cloud will collapse if gravity dominates, and if the pressure dominates, it will either expand or it will start oscillating. So cooling basically decreases the pressure, so it will assist collapse. Now, as the cloud starts collapsing, it should not be that it collapses just to a black hole. Okay. So as the cloud collapses, its density keeps on increasing, and its Jeans mass decreases, and this will lead to formation of smaller clouds, and that is called fragmentation. So the gas will basically fragment into small clouds. Now, this fragmentation also should not continue forever, otherwise you will be left with very small clouds, and that is what we don't see in our universe. So at some point what will happen is, as the density keeps on increasing, the cloud will become so dense that the example I gave, that there is a transition and there is a photon coming out, that photon won't be able to escape the system. If the photon doesn't escape the system, you are not losing the energy. Okay, so basically this cooling at some point stops when the cloud becomes very dense and hence what we call optically thick. The collapse halts, and it is possible to do a calculation to see at what masses will the collapse stop, and you will be able to show that for typical cooling mechanisms, the collapse will stop around a mass scale of a solar mass. Of course, that's the order of magnitude calculation, but now people can do these things in much more detail using models, and then that will be followed by like more complex physics taking over, basically then there will be formation of other elements, molecular clouds, and so on, and essentially leading to star formation. And once star starts to form, and that at the same time the galaxy also evolves, the galaxy forms, and hence those are the galaxies we see. But the basic idea is all these things are happening in dark matter halos. That is the first point to understand. The second point to understand is not all dark matter halos will be able to cool and form stars. For example, if the dark matter halos don't have enough kinetic energy to have the initial excitation of atoms, then it won't be able to cool. So there are issues, and that is what gives rise to so many interesting physics. In fact, there is a lot of things you can study about the galaxies through what is known as the luminosity function, and I will give you a very simple example which is easy to understand. For example, you have done a galaxy survey, so you have measured luminosities of the galaxies in some particular band. So you calculate what is known as the galaxy luminosity function. So that's the number of galaxies per unit volume per unit luminosity range. So this is one of the measurements of the luminosity function. So the x-axis is luminosity. What has been written here is in terms of magnitude. Okay? So observers prefer to work with magnitudes, which is basically a measure of the luminosity. And this is that luminosity function. Plotted as a function of not the luminosity but magnitude. Okay. And this is how it looks like. These correspond to the brighter galaxies, these correspond to the fainter galaxies. One can go actually and go make a fit to the data, and then there is something called a Schechter fit which works very well. Now, we know theoretically the halo mass function. I, for example, gave you some idea about how to calculate the number of halos per unit volume per unit mass range. Observations are giving you the number of galaxies per unit volume per unit luminosity range. Can we use, there is a theory and there is observation, can we use them to connect the luminosity of the galaxies to the mass of the halo? That would be a very interesting thing to see, that what kind of halo masses produce what kind of galaxies. Okay. So this is the idea that the galaxy numbers must be related to the halo numbers. So let us take a simple scenario, and this is really a simple scenario. We know that this scenario is too simple. The actual scenario is much more complicated, but this I want to show you how even simple models can be constructed. So you say that each halo forms one galaxy. You then also say that the luminosity of the galaxy is, okay, not proportional, but it is like, okay, let us say it is proportional to the halo mass. Okay, so if the halo mass doubles, then the luminosity also doubles. Very simple model. So in that case, I can write luminosity to be some constant times the halo mass, and then I know the halo mass function. So that will immediately give me the luminosity function of galaxies. Okay. So now, what will happen is, what you will get is this. So if you look at this, the observations are the blue curve. This is basically the Schechter fit to the observations in the previous slide which I did. If I use this model, I then varies this constant, the free parameter. Let us say this is the free parameter of the model. I keep on varying that. And at best, I can get something like the red curve. So I clearly see the simple model does not work. Okay, so the red curve is not a good description of the blue curve. Okay? No matter what I do, I change zeta to whichever value I want. It's simply either it will, if I try to match this end, then it will be a very bad match on that end, and so there's no way I can do anything. Now, but this, suppose now I say, what do I need to do to match? What I need to do is I need to put these galaxies here, which are in the theory, the galaxies along this line. I need to bring them closer to the blue line. So I have to basically make them fainter. Okay, remember this way, if you go this way, it becomes faint. Similarly, these galaxies also, I need to make them fainter, but not by the same amount. If I could do it by the same amount, then it would be just like changing the value of the zeta. So I have to make these galaxies fainter, and maybe leave these galaxies untouched. Okay. This, of course, I have motivated this from a simple scenario. But more detailed models of galaxy formation will also suffer from a difficulty like this. Now, let us try to make a slightly complicated model. But it is complicated but still simple. What we say is, earlier we said that the luminosity is proportional to the halo mass. But we say that no, now we relax that assumption. And we say that it is a relation which is free. But we just say that it is monotonic. High mass halos should have brighter galaxies and vice versa. Then we ask, what relation do I need to match the data? And this can be done properly. And this technique is not called abundance matching. Now I have asked what do I need to match the data. This is what I need to match the data. This is what has been plotted here is the mass of the halo versus magnitude of the luminosity, and you can see they are not proportional to each other. I need something which looks like this. To get more insight, what I do is I plot the luminosity versus luminosity divided by halo mass, and x-axis is the magnitude of the luminosity. So if this was constant, that would be the earlier model which did not work. What I get is that you see it has a kind of bell-shaped peak. As I was saying, I have to make the brighter galaxies fainter. I have to also make the fainter galaxies fainter, and that is clearly shown in this plot. So basically, both the low mass halos and the high mass halos should form stars rather inefficiently, so that this curve goes down in this side, this curve goes down on the other side. Now, physically, we now know why this happens. This happens because of a process called feedback. So, in the low mass halos, there is something called a radiative or reionization feedback or supernova feedback. So, basically, what happens is that because of these feedback effects, the gas gets heated up, and then they are not able to cool anymore. Or sometimes the gas can get expelled from the halo. So star formation suffers a lot. But that does not happen in the large mass halos. In large mass halos, something else happens. That's called the Aegean feedback. So basically, if Aegean forms, if the nucleus of the galaxy becomes active because of the central supermassive black holes, then there could be various activities, jets flowing and so on, and that may basically kill all the star formation which were going on in the galaxy. So this simple kind of arguments actually you can see already tells you a lot of physics which would have been happening inside the galaxies. But yes, I mean, to do the actual stuff, you have to go and do all this modeling numerically. You cannot just use simple. Simple models are useful to get the initial idea about what physics might be going on. But to actually go and match the observations using full everything put in, you have to do much more detailed numerical modeling. And that is the kind of state of art which goes in the galaxy formation community. I have been talking about the luminosity function. That is like just measuring one property of the galaxy and plotting the distribution of that. You can also do clustering of galaxies. So you can say that if I find one galaxy here, what is the probability of finding another galaxy at a distance, whatever distance you choose, 1 megaparsec, 5 megaparsec, 10 megaparsec. Yeah, and then you plot that as function of distance. So that will be the 2-point correlation function. So you measure the clustering of galaxies, okay, the 2-point correlation function of the power spectrum. But will that power spectrum be same as the dark matter power spectrum? Because dark matter power spectrum is something we understand from our theory. Now what happens is just analogous to the correlation function of dark matter, which is like you take the density at point 1, density at point 2 and take the ensemble average. You can also calculate the correlation function for halos or galaxies. So you say that what is the probability of finding a halo of mass m1 at point x1 and another halo at point x2 having mass m2. You can play this game, and what you can show is that to the linear order, the density contrast of halos are related to the density contrast of the underlying dark matter by a formula which looks like this, where nu is nothing but the critical density at collapse, which I discussed in the last class, divided by a variance of the density field. This variance is nothing but an integral of the power spectrum with an appropriate window function. So this gives rise to what is known as halo bias, and that is basically defined through the relation like this, which says that the density contrast of halos is bias times the underlying density contrast. And because of the way sigma m behaves, what happens is this bias will be larger for larger mass halos. And then you can calculate the 2-point correlation function, which will be combination of these bias parameters times the underlying dark matter. So the whole point of this calculation is to tell you that if we measure, for example, the correlation function of the halos or the correlation function of the galaxies, they will be related to the underlying dark matter correlation function, but they are not equal to the dark matter correlation function. There are extra factors which go and sit in. These factors essentially depend on what kind of halos are hosting those galaxies. So you have to know a bit more. So what you will get is a measure of the dark matter correlation function, but a biased measure of that. That is why this is called a bias. And similar relations you can derive for the power spectrum as well. These are, for example, some results from simulations. There are many such simulations. I have taken just one of them. And these are for different redshifts. The black one is the dark matter correlation function. Okay. The red one are the halo correlation function, and the green one are the galaxy correlation function. So generally you see that at high redshift, the galaxy correlation function is higher than the dark matter correlation function. That means if you find a galaxy somewhere, there is more probability of finding the galaxy nearby compared to the underlying dark matter distribution. Okay, so this is a feature of this kind of random fields. This, of course, has also been observed. The previous slide was for simulations. This is for observations. I have taken the SDSS result. So here, what has been plotted here is a measure of the correlation function. It is an integral of the correlation function. Okay, so it's called the projected correlation function. This has to do with the fact that we observe the galaxies only in the projected sky. What has been plotted here is the correlation function of the galaxies. So this is the correlation function versus distance for galaxies of different magnitudes. Okay, so these ones, these red, magenta, are the brighter ones. These are the fainter ones. And you can see for the fainter ones, the clustering strength is small. For the brighter ones, the clustering strength is large. So clearly, the brighter galaxies are more biased than the fainter galaxies, which means the brighter galaxies are probably forming in preferentially large mass halos, which connects with kind of things we have been discussing so far. I mean, this is essentially a similar plot showing how the bias basically changes with luminosity. You can also, what you do is you can also ask the same question in terms of colors. So this is the correlation function, but in terms of colors of galaxies. So the black one is all the galaxies. And then if you take the red galaxies, you get the red line. And if you take the blue galaxies, you get the blue line. So you can see the red galaxies seem to have more clustering than the blue galaxies. So again, if I think in terms of halo masses, probably the red galaxies are sitting in larger mass halos. So this is the kind of insights you get by studying the correlation function. Okay? And this is how the game is played. And then you can go and now do very complicated simulations of galaxy formation and try to match with the observations, and you will actually infer results which are similar. And then this is something we discussed in the first lecture. You can go and measure the acoustic oscillations in the power spectrum. So what has been plotted here is the power spectrum now instead of the correlation function. And the power spectrum shows these oscillatory features. So this is arising because of the fact that the baryons were interacting with photons when the CMB was formed, and now the baryons remembered that activity even now. So even if we go and observe the galaxies nearby, they will show up these features. Now, actually modeling galaxy formation is a tall task. So if you try to do galaxy formation simulations, you will be talking about a wide range of physical processes. Okay, and some of these I was discussing, starting from gas cooling to how the interstellar medium forms, star formations, the feedback, again something I talked, the supermassive black holes, which actually give rise to some of these feedback, and the active galactic nuclei. Then things which I did not talk about are the magnetic fields, how the radiation field changes, and so on. And each of these are basically done using a different kind of prescriptions. and then it depends on how you actually model them numerically. So all these things become very important. So there's no point in going through this slide in great details, but this is just to give you an idea the complications which are involved in simulating the galaxies. This is something I showed you yesterday, that there is a lot of simulation which has already been done for galaxy formation, and there are some simulations which are called zoom simulations. Basically, you focus on one or two individual galaxies and try to figure out what is going on there. And then there are simulations which study the large volume, where galaxies are just a small part of that, but you can see the galaxies which are where they will form. But you can also study the large scale structure of the galaxies, and there are various ones which are interesting here. Some of them are public, some of them are not. Now, this was what I wanted to talk about regarding galaxies. There is a whole set of other observations which have nothing to do with galaxies but can tell you about large scale structure. So to motivate that, let us ask that we have already calculated the number of halos per unit co-moving volume in a mass range. So I can calculate the total amount of mass contained in halos. Okay, so that will be just this integral. I take all the halos, multiply by their mass, and then integrate. I can then divide by the total volume. That will give me the mass per unit volume in collapsed halos. And then I can divide by the total density of the universe. That will give you the fraction of mass that is in collapsed halos. And you will see that for most cases, particularly at high redshift, so what has been plotted here is the collapsed mass versus the mass of the galaxies, mass of the halos. And you can see for most part, the matter is actually outside the collapsed halos. For example, suppose for definiteness, let us choose redshift equal to 2, the green curve. So green curve, you see at best you can have 30%. I mean, if you take all the small mass halos which can potentially form galaxies, you can at best have 30% of the mass inside galaxies, and it could be much less. So actually most of the matter is sitting outside the galaxies, in between the galaxies in this cosmic wave. This forms what is known as the intergalactic medium. The difference between the galaxies and the intergalactic medium is that the intergalactic medium has not collapsed. So the densities are not very high. So, and they are essentially tracing the underlying cosmological density field. So clearly there is a lot of information in the intergalactic medium also, because they are containing a large bulk of the cosmic matter. So basically the intergalactic medium contain majority of baryons, particularly at high redshifts. Since it is of low density, the physics required is less complicated. So you can bypass a lot of the complex physics you need to model galaxies because those are not happening in these low density regions. There is also constant interaction between the galaxies and the intergalactic medium. For example, all the gas which are in galaxies today were in the intergalactic medium at high redshifts, and then basically they collapsed and formed halos and gas and so on, the galaxies and so on. Also, once you form galaxies, various events happen like supernova feedback or Aegean feedback. And if you set up all these outflows of gas because of these energies inside galaxies, they will eject matter into the intergalactic medium. So IGM and the galaxies are constantly interacting, and that also is very important for understanding galaxy formation and evolution. Now, IGM is good, but how do you probe it? One of the best probes of the intergalactic medium is using quasar spectra. So you have these distant quasars, and light from them are coming towards us, and they are absorbed by the intervening medium. Now, if you want to study how the light from the quasar is coming from quasar to us and how the intensity is getting changed, you need to solve what is known as the radiative transfer equation, and this is the radiative transfer equation. It is a differential equation involving the specific intensity, and it tells you how the specific intensity evolves as light is passing through. And the specific intensity evolves because of absorption, which is the first term, and emission, which is the second term. Now, if you want to solve this equation in an expanding universe, this equation picks up additional terms. For example, you need to account for the fact that because of the expansion of the universe, there will be a dilution because the volume is increasing. Also, there will be redshifts. Okay, so intensity which started in one frequency will not remain in that frequency. It will basically, the frequency will decrease and it will go to some other frequency band. So accounting for these, you can actually go and solve these equations. So for simplicity, let us assume there is no emission along the line of sight between the quasar and us. So light starts from the quasar, comes to us, and what can only happen are absorption. In that case, it is easier to solve this differential equation. This kind of partial differential equations are best solved by the method of characteristics. So the intensity which you will receive will be the initial intensity times some volume dilution factor times the exponential in a minus of a quantity which is called the optical depth. So that is basically the optical depth. That is the integral of the absorption coefficient along the line of sight. Okay. So what you observed is the initial intensity times e to the minus tau. So all the information about the absorption, whatever is happening, is encoded in this optical depth tau. Tau can be calculated. For example, if you think that the absorption is happening because of neutral hydrogen, then you can calculate the corresponding optical depth. What will happen is it will be a line integral of the neutral hydrogen density, okay, because the absorption will be proportional to how much neutral hydrogen you have, times the absorption cross section. So that will tell you what is the probability of getting a photon absorbed. But then you have to account for the fact that there will be redshift. So that is why what you observed at frequency nu will actually be absorbed at a different frequency. Okay, so that you have to account for. For example, the most prominent absorption is what is known as the Lyman alpha transition. Lyman alpha transition is nothing but if you have neutral hydrogen atoms in the ground state, a photon comes of appropriate frequency, it kicks the ground state electron from to the first excited states, n equal to 1 to n equal to 2. That is called the Lyman alpha transition, and that will happen if the photons have very specific frequencies. So basically the cross section is almost like a delta function, not quite, but let us for simplicity assume that it's a delta function. And the delta function will peak at frequencies which correspond to the energy difference between the n equal to 1 and n equal to 2 line. In fact, the corresponding wavelength is 1216 angstrom. That is a basic idea. So if you put in this cross section here, you will be able to calculate the Lyman alpha optical depth, and Lyman alpha optical depth is basically given by the Lyman alpha cross section, because the more the cross section, more will be the probability of absorption, and hence the higher the optical depth. There is a cosmology factor coming in because you are basically passing through the cosmological distance, and it is proportional to the number of neutral hydrogen atoms you have. And the observed density is basically the unabsorbed density times e to the minus tau. This is, for example, one typical quasar spectra. So, for example, this is the observed wavelength versus the intensity, observed intensity. You see a prominent emission feature. This emission feature is happening because of something inside the quasars or inside the active galactic nuclei. And this happens at a wavelength 1216 angstrom in the rest frame of the quasar. But we observe it as a different wavelength, and that is because the quasar is at a redshift, very close to 3 in this case. Okay. So this is what I mentioned here, that something which is happening at 1216 angstrom at the quasar rest frame, we will observe at a different wavelength, which is nothing but 1216 angstrom multiplied by 1 plus z. Now, what happens is all these photons, which are like having wavelength smaller than the Lyman alpha, they have a wavelength smaller than the Lyman alpha, so they start from the quasar and is coming towards us. But at the same time, the universe is expanding. So as the universe is expanding, their wavelength gets expanded. That is the redshift effect. So these photons will have, as I said, initially wavelengths which are smaller than Lyman alpha. So if they expand, they will hit Lyman alpha at some point. And at that point, if they encounter hydrogen atoms, neutral hydrogen atoms, they will get absorbed because the neutral hydrogen atom will absorb that photon and go to a higher excited state. So one can work this out through an example to understand, but that is the basic idea. So the whole thing to understand is that all these absorption lines are happening because the photons are getting absorbed by the intervening neutral hydrogen. So these absorption lines, their distribution, their strength is telling us how the neutral hydrogen is distributed between the quasar and the us. And neutral hydrogen, if it traces the underlying matter distribution, which it does, then using these absorption features, we can study the large-scale matter distribution in the universe. If I can study the large-scale matter distribution of the universe, I can do all the statistics, I can calculate the power spectra and so on. And that is how large-scale structure are studied using the intergalactic medium. So you clearly see here we are basically tracing the diffuse gas. Okay, we are not doing large-scale structure using galaxies, but the intergalactic medium. So if I write the optical depth, which is the measurable quantity, as I said, that is proportional to the neutral hydrogen density. But the neutral hydrogen density is essentially proportional to the neutral hydrogen fraction times the underlying density, which is this. This is the 1 plus density contrast of the baryonic field. The idea is, since the optical depth has information about the underlying density field, then using the optical depth fluctuations, I can study the density fluctuations, and through the density fluctuations, I can calculate the power spectrum. That is how people estimate the matter power spectrum using the Lyman alpha forest. For example, these points are using the Lyman alpha forest. Lyman alpha forest, the advantage is you can actually calculate the power spectrum at much smaller scales, which are otherwise difficult using galaxies. Okay. The difficulty, the challenge in these observations is that whatever the observed quantity is not only dependent on the underlying density field, but also the neutral hydrogen fraction, and the neutral hydrogen fraction depends on whatever astrophysics is going on in this intergalactic medium. So you have to be very careful. Either you have to model this astrophysics carefully, or you have to marginalize over all the uncertainties. The advantages of Lyman alpha forest is, since high density regions tend to occupy smaller volumes, the lines of sight to the quasars have very low probability to pass through the high density structures. Okay, if you shoot a random line of sight, the probability of it cutting through a high density region will be very small. It will actually most of the time be passing through the low and medium density cosmic wave. So it can be modeled using much less resources. Your simulations can be much faster, or you can even use something like a quasi-linear theory to model it. Nowadays, they are all done using simulations, but those simulations are much less expensive than the galaxy formation simulation. Using Lyman alpha forest, there are many other things about the universe you can learn. For example, suppose I take this optical depth and actually put in the values and calculate the numerical value. So I put in the values of the cosmological parameters. What I will find is that the optical depth is 10 to the 5 times the neutral hydrogen fraction times 1 plus the density contrast. And suppose I average over a large volume, so the average density contrast will go to 0. Then the optical depth will be 10 to the 5 times the average neutral fraction. Okay. So now think about, let me just go back a bit. Think about the observable. Observable is this intensity, which is the unobserved intensity times e to the minus tau. Now, if tau is even, say tau is 10, just to give you an example, e to the minus tau will be a very small quantity, and I nu will just go to 0. But here we don't see it going to 0. We see it, we see lots of features. Okay, it is just not consistent with 0 at all the points, which means tau cannot be too high. And if tau cannot be too high, then that means that the neutral hydrogen fraction has to be of the order of 10 to the minus 5. if the neutral hydrogen fraction is like even 10 to the minus 3, let us say, then tau will become something like 100. If tau becomes 100, then e to the minus tau, you can calculate what it is, it will be just 0. So since we don't see it to be 0, that means the universe must be very highly ionized. Okay. So we do not observe complete absorption, which means the universe is highly ionized at redshift 3, wherever we have observed. This is known as the Gunn-Peterson effect. Actually, this conclusion is valid from like today's universe to about redshifts of 6. So basically, the quasar absorption system is telling us that we are living in a universe which is very highly ionized. The Lyman alpha forest, this part, just to again, no, it's a question of nomenclature. This part of the quasar absorption spectra is called the Lyman alpha forest because these lines are arising because of Lyman alpha transition, and there is a forest-like feature. This absorption line shows up like a forest. So that is why it's called the Lyman alpha forest. And using Lyman alpha forest, we learned that the universe is very highly ionized. The Lyman alpha forest close to redshift 6 looks very different. So you can see this is that same Lyman alpha emission line. And here you would have expected the Lyman alpha forest, but you simply don't see that. You see everything consistent with 0. So here things start to become complicated, and we are probably looking at a universe which is slowly becoming neutral. So now the idea is the universe is ionized today from redshift 0 till about redshift 5.5 and 6, and then it is probably neutral. So this tells you another effect of structure formation, which is the reionization of the universe. This is happening because of the first structures in the universe. So the idea is that the universe becomes neutral for the first time at redshift 1100. That is where the CMB originates from. However, the Lyman alpha forests are implying that the bulk of the universe is highly ionized at lower redshifts. So basically, what has happened is the ionizing photons produced by the early stars have again ionized the universe, and that is known as the reionization. This reionization is a very important field of study. It is also called kind of the final frontier of observational cosmology. People are trying to go and observe it, and it can be observed using Lyman alpha absorption. It can be understood using CMB anisotropies, and in the future, something called 21 centimeter radiation. In fact, the reionization optical depth is one of the cosmological parameters in the concordance model of cosmology. So if you remember our first lecture where I listed the cosmological parameters, you had omega matter, omega baryon, Hubble parameter, and so on. And one of the parameters was tau, which is entirely due to reionization. So reionization, you can see, plays an important role for cosmological parameters as well. So the final slide is basically a movie which gives you an idea about what reionization is. So the left-hand slice is basically the structure formation happening, and you can see wherever there are high densities, these whitish regions are the places where galaxies will form. The right-hand side shows you the distribution of neutral hydrogen. Red ones are neutral and the black ones are ionized. And you will see wherever you are forming galaxies, those regions in hydrogen are becoming black, meaning they are getting ionized. And then these ionized regions are growing and kind of overlapping, and then the whole universe at some point gets ionized. This is, of course, a model, a theoretical understanding. And hopefully, with future observations, we will be able to kind of understand and verify this picture. And this, again, is a probe of the first structures which formed in our universe, the first times the stars and the galaxies formed. So I think this is a good place to stop. And if there are other questions, I can now take them.
Hello.
Yeah, go ahead.
This is Subrat. Am I audible?
Yes.
Yeah, I was just maybe I missed it somewhere during the talk. My question is the galaxy formation and the star formation within the galaxy. Do they happen kind of simultaneously? During the same time, um, or something happens earlier. I mean, stars form earlier and than the galaxy, or I mean,
I, I mean, the full details
how
are not
maybe
understood. It depends on, I mean, how you define the
comment
galaxy.
on
So, if you think of the galaxy as all these very nice spiral arms and so on forming, so it is not clear which forms earlier and which forms later. It could be a mix of
okay.
things. I mean, the stars will form, and probably around that time, the galactic dynamics are also going on. So stars at some point will settle down on a disk, which will form and then eventually form the spiral arms and so on. But that doesn't mean the star formation stops. Okay, then there will be other generations of
No,
star
I mean,
forming. So it is much more complex than one
I-
happening before the other.
okay,
Yeah.
okay. It's not like we maybe it's a kind of wrong impression to think that there is a supermassive black hole at the center, and then the stars are around, and the supermassive black hole then
No,
gravitationally
no,
pulls the stars along.
it
No,
is
it's
not
not
that
like that.
simple. It's
It's
not
not
that
that
simple.
simple.
I mean, if
Uh,
it is not that simple. It
okay.
may be possible that something like this happens at galaxies which formed much late, because the
Okay.
supermassive black
Okay.
holes may be there because of earlier mergers of
Yes.
galaxies. This
Yes. Yes.
cannot definitely be the case for the early galaxies,
Early galaxies. Yes. Yes.
because the
Yes.
supermassive black hole may not have even formed by that
Formed right. Yes. Yes. I
time.
agree. Yes.
So it is much complicated than that.
Okay. 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 Thank you.
Okay. Is there are there other questions? You can either put it on the chat or you can raise your hand or just unmute yourselves. There's something on the chat. So somebody is asking, according to the ergodic hypothesis, ensemble average is equal to the time average. Is that applicable here? No, it's not time average here. It's the ensemble average. In this case, is equal to the volume average. Okay, so that is the only change which needs to be made here. So time average is not applicable here. It's a volume average which is applicable here. Ensemble average is equal to the volume average.
Yeah, I had a question in this connection. So, in
Mm-hmm.
order to calculate the volume average, we need to assume some kind of density distribution, right? Or
No, no. You just go to some go here, set up some volume, and
okay.
calculate what is the average density there, because you are seeing whatever it is in the observations.
So okay. Then the question is, whatever we are observing, let us say in the CMB sky, CMB universe, whatever we are observing, we have to put it in the mathematical form to calculate the volume average. Is it not?
No, you can calculate the volume average directly.
Numerically when you do it. Okay.
Numerically, yeah. You just, I mean, in the simplest case, you just add up. I mean, suppose you want to
Yeah.
calculate the number of galaxies per unit volume, or the volume average of the number of galaxies. You count the galaxies and then just divide by the volume. So that
Right.
will give you the number density. So that is the volume average. The thing is, of
Okay.
course, I mean, using the CMB sky, we can calculate the distribution of the density field, and that turns out to be Gaussian. Unfortunately,
Okay.
at lower redshifts, it is not Gaussian anymore because of nonlinearities, because various things have happened. Okay. So the nearby universe is not Gaussian,
Okay.
but the linear density field when the amplitudes were small were Gaussian. Okay.
Mhm.
Yeah.
Got
Any
it.
other questions?
Okay.
So, okay, somebody has asked, Divakar has asked, how do we get baryons from dark matter? We don't. Baryons and dark matter are different. Okay, if there are no further questions, shall we stop for now? Okay, so yeah, thank you all for listening to the lectures. So I will then stop sharing.